Welcome to this topic on astrophysics. Astrophysics is the study of objects and processes beyond Earth. It uses physics to explain stars, planets, galaxies, and the universe as a whole. In this topic, we will explore how stars form, evolve, and how scientists measure the vast distances in space. Astrophysics in the A-level specification, overview of observational astronomy. Astrophysics is an optional topic and focuses on applying fundamental physical principles to understand the universe. The topic integrates ideas from waves, mechanics, fields, and thermal physics to explain how astronomers observe and interpret distant celestial objects. A key emphasis of the specification is not only what we know about stars and galaxies, but how we know it. Students are expected to understand the physical principles behind telescopes and detectors, as well as the interpretation of data such as spectra, brightness, and redshift. Observational astronomy is the branch of astrophysics concerned with collecting and analyzing electromagnetic radiation from celestial objects. Because stars and galaxies are extremely distant, astronomers cannot experiment directly on them, so almost all knowledge comes from analyzing received radiation. The Earth's atmosphere only allows certain wavelengths, mainly visible light and radio waves, to reach the surface, which is why space-based telescopes are required for infrared, ultraviolet, X-ray, and gamma-ray astronomy. Visible light reveals surface features and color, infrared can penetrate dust clouds and reveal star-forming regions, and X-rays are produced by very high-energy processes such as accretion onto black holes. Observational astronomy relies heavily on accurate measurement of intensity, wavelength, and angular position. Refracting telescopes using converging lenses, reflecting telescopes and the Cassegrain design, non-optical telescopes across the spectrum, resolving power and the Rayleigh criterion, collecting power and CCD detectors. A refracting telescope consists of two converging lenses, a long focal length objective lens and a short focal length eyepiece lens. In this arrangement, parallel rays from a distant object are brought to a focus at the focal plane of the objective lens, forming a real, inverted image. This image is then viewed through the eyepiece, which acts as a magnifying glass to produce a final virtual image at infinity, allowing the eye to observe without strain. Reflecting telescopes use mirrors instead of lenses to collect and focus light. The Cassegrain arrangement, which consists of a large concave parabolic primary mirror and a smaller convex secondary mirror. Incoming parallel rays are reflected by the primary mirror towards a focus, but before they reach it, they are reflected back by the secondary mirror through a hole in the primary mirror to the eyepiece or detector. Reflecting telescopes have several advantages. Mirrors do not suffer from chromatic aberration, they can be supported from behind, allowing much larger diameters, and they are generally cheaper to manufacture. Spherical aberration is minimized by using a parabolic mirror. Most large research telescopes, such as the Very Large Telescope in Chile, are reflectors. Astronomy is not limited to visible light. Students are required to understand single-dish radio telescopes as well as infrared, ultraviolet, and X-ray telescopes. Radio telescopes are similar in principle to optical reflectors but operate at much longer wavelengths, meaning they require very large diameters to achieve reasonable angular resolution. Many radio telescopes are positioned in remote areas to reduce interference. Infrared telescopes are often placed on high mountains or in space to avoid absorption by atmospheric water vapor. Ultraviolet and X-ray telescopes must be space-based because these wavelengths are absorbed by the Earth's atmosphere. Each region of the electromagnetic spectrum reveals different physical processes, such as cold gas clouds in radio astronomy or extremely high-energy events in X-ray astronomy. The resolving power of a telescope describes its ability to distinguish between two closely spaced objects. Due to diffraction, even a perfect optical system produces diffraction patterns rather than sharp points. The Rayleigh criterion states that two-point sources are just resolvable when the principal maximum of one diffraction pattern coincides with the first minimum of the other. The minimum angular resolution is given by theta almost equal to lambda d, where lambda is the wavelength of light and d is the diameter of the objective lens or mirror. Resolution improves with shorter wavelengths and larger diameters, explaining why large telescopes are essential for detailed astronomical observations. Collecting power refers to a telescope's ability to gather light, which is proportional to the square of the diameter of the objective. A larger collecting power allows astronomers to observe fainter objects and obtain better signal-to-noise ratios. CCDs have a much higher quantum efficiency, meaning a greater proportion of incident photons are converted into usable electrical signals. They also allow long exposure times and digital storage of data for later analysis. Apparent magnitude and brightness, absolute magnitude, and astronomical distance blackbody radiation and stellar temperature, spectral classes, and absorption lines. Apparent magnitude is a measure of how bright a star appears from Earth and is a subjective scale based on human perception. In the Hipparcos magnitude scale, smaller or negative values correspond to brighter objects, and the dimmest stars visible to the naked eye have a magnitude of about +6. The scale is logarithmic. A difference of 1 magnitude corresponds to an intensity ratio of approximately 2.51. Apparent magnitude depends on both intrinsic luminosity and distance. Absolute magnitude, m, is defined as the apparent magnitude a star would have if it were placed at a standard distance of 10 parsecs. This allows astronomers to compare the true luminosities of stars independent of distance. The relationship between apparent magnitude m, absolute magnitude m, and distance d in parsecs is given by m equals 5 log d10. The parsec is defined as the distance at which one astronomical unit subtends an angle of 1 arcsecond, and is approximately 3.26 light-years. Stars are approximated as blackbody radiators, meaning they emit a continuous spectrum that depends only on temperature. The shape of a blackbody radiation curve shows that hotter objects emit more energy at all wavelengths and have a peak at shorter wavelengths. Wien's displacement law, max T equals 2.9 times 10^3 mK, allows the surface temperature of a star to be estimated from the wavelength of maximum intensity. Stefan Boltzmann's law, P equals at 4, relates the total power radiated to surface area and temperature. Stars are classified into spectral classes O, B, A, F, G, K, and M, ordered from hottest to coolest. Each class has characteristic absorption lines due to the elements present in the star's atmosphere and the temperature-dependent excitation of atoms. For example, strong hydrogen Balmer absorption lines are seen in A-type stars because many hydrogen atoms have electrons in the N equals 2 energy level. Cooler stars show absorption from molecules such as titanium oxide. The Hertzsprung-Russell diagram, life cycle of low and high mass stars, supernovae, neutron stars, and black holes. The Hertzsprung-Russell (HR) diagram is a key tool for classifying stars and understanding stellar evolution. It plots absolute magnitude or luminosity against temperature or spectral class, with temperature decreasing from left to right. The main sequence runs diagonally across the diagram, where stars spend most of their lifetimes fusing hydrogen into helium. Stars form from nebulae as gravitational collapse increases temperature and pressure until nuclear fusion begins. Low-mass stars, like the Sun, evolve into red giants before shedding outer layers and leaving behind a white dwarf. High-mass stars undergo more dramatic evolution, forming red supergiants and ending their lives in supernova explosions. Supernovae are powerful stellar explosions marked by a rapid increase in absolute magnitude. Type Ia supernovae have a characteristic light curve and are used as standard candles to measure astronomical distances. Neutron stars are extremely dense remnants composed almost entirely of neutrons, while black holes are objects with escape velocities greater than the speed of light. The Schwarzschild radius, Rs almost equal to 2 gm-c2, defines the size of a black hole's event horizon. Gamma-ray bursts and supermassive black holes at galactic centers. The Doppler effect and redshift, Hubble's law, and evidence for the Big Bang. The Doppler effect for light describes how the observed wavelength or frequency changes when a source moves relative to an observer. In astrophysics, redshift occurs when light from distant galaxies is shifted to longer wavelengths, indicating that they are moving away from Earth. For relatively small velocities, redshift z is given by z equals lambda almost equal to v(c). Hubble's law states that the recessional velocity of a galaxy is proportional to its distance from Earth, v equals h0d, where h0 is the Hubble constant. This relationship provides strong evidence that the universe is expanding. By extrapolating backwards in time, astronomers infer that the universe began from a hot, dense state known as the Big Bang. In astrophysics, we use physics to understand the universe. By studying light, spectra, and the behavior of stars, scientists can discover how stars form, evolve, and how the universe has changed over time. Thank you for watching.